you can use that camera frame.
Yep.
So homework 1 was due today. Did everyone turn that in? Submit that to Blackboard? Upload that? Okay. 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 So try to remember that in the future. I'll accept it late today, but not in the future. So a couple other things about, we're talking about Fourier transforms.
Do you want to try turning off the lights in the booth?
What?
Do you think that might help the video, is turning off the board lights?
I'm not sure.
Or turn off the main lights and keep the board lights on.
Yeah, or some, I just feel like it's really light against the white chalk. Okay, that's worse.
So the other way around, we need to make that.
Oh, that's better. Can't tell if you can really see it though.
Yeah, that's what the notes are for. We're trying to get cameras that actually, pan and come closer to the board, but we're not there yet. So we'll talk about some basic Fourier transforms. Today we'll talk about Fourier transforms of periodic signals, and then also a brief review of linear systems. So consider a periodic signal T, and then I use capital T0 to represent the period. And just assume it looks like this. The shape doesn't really matter. The result will hold true for any periodic transform. So it's infinite in both directions with a period of T0. T0 over 2 minus T0 over 2. Now, we define what's known as the generator function. And then this is really a mathematical description of the entire periodic waveform, but just over one period. And the most convenient period here to use is between minus T0 over 2 and T0 over 2. But let's call that section G of T. So this little portion, I'm not going to draw a separate graph with just that, but a graph of GT would just be this triangle and then 0 everywhere else. Okay, so G of T is just that portion of this entire periodic waveform. And what we want to do is actually come up with an expression for the Fourier transform of G of T0 in terms of the Fourier transform of G of T. We can write G of T0 as just an infinite sum of shifted versions of G of T. So then it's taking our generator function, and with m equal to 1, it would be shifted to the right later in time by T0. With m equal to 2, we get this one, 3, and so on. With m negative, it's shifted to the left. So it's just a convenient mathematical representation of a periodic waveform in terms of the base function or the generator function. Because it's periodic, it has a Fourier series, and the Fourier series representation is a sum from n equal minus infinity to infinity of Cn e to the j 2 pi n f0 t. Now, this expression didn't come from the one above it. This is the general expression for this Fourier series of any periodic waveform. This is the exponential representation of the Fourier series, where Cn are the Fourier series coefficients, and we get those. You can actually integrate over any period. We'll choose the period from minus t0 over 2 to t0 over 2 of g of t0, but in this interval, g of t0 is just equal to g of t, our basis function. E to the minus j 2 pi n f to the t dt for 1 over t0 is f0. Minus infinity, infinity. I can extend the limits of my integration because gt is 0. Normally we do this in reverse. Gt is just limited to the range, to the region minus t0 over 2 to t0 over 2, so I can reduce my limits of integration. Here I can just extend them because gt is 0 outside that range, and so these intervals are equal. And that's really t, dt. But if you look at this, might look familiar. This looks like the Fourier transform of g of t, the interval. Okay, so the Fourier series coefficients are actually related to the Fourier transform. Fourier transform, I think that, yeah, that's roughly in there. And Fourier transform would have an f here. So if I evaluate the Fourier transform at the frequency nf0, one particular frequency, then I can get an expression for the Fourier series coefficients from the Fourier transform. We didn't actually do this in 310, but it is a convenient way to get the Fourier series coefficients. Evaluating this interval to these Fourier series coefficients is usually pretty hard, right? We've got tables of Fourier transform. So this gives you an easier way to get Fourier series coefficients. Find the Fourier transform of the generator function or the basis function, evaluated at one particular frequency. Okay. Or actually multiple frequencies, because n is 1, 2, so it goes from minus infinity to plus infinity, but it's an infinite value. So evaluated at those frequencies to get an expression for the Fourier series coefficients. So T0 of t then is taking this and plugging it into a Fourier series expression. Minus infinity to infinity. T n f0 e to the j 2 pi n f0 t. So that's actually just the Fourier series expression for the periodic waveform. But now we can take the Fourier transform of this which I have one expression for it as shifted sum of my basis functions. Infinity, minus n0. But now, taking the Fourier transform of this, that's got to be equal to infinity, f0. And the Fourier transform is linear. So the Fourier transform over sum is the sum of the Fourier transforms. This is just a constant. is I just have the Fourier transform of, this is the only function of time, and that's an impulse. The Fourier transform of e to the j omega 0 t is just, or I f0 t is just delta f minus f0. So this becomes delta f minus n f0. As an expression for the Fourier transform of a periodic system. The Fourier transform consists of, this is actually a sum of shifted impulses. So what this would look like, if I sketch this thing on f-axis, there's an impulse at the zero component at n equals 0, so we have delta f, so that would be of height f0, v0, and then at f0, the height would be f0, t, f0, and some at minus f0, and 2f0. I don't know what the heights of these things are. The heights actually depend on the Fourier transform of the basis function, the generator function. I evaluate that at 0, f0, 2f0. Actually, these would be the weights of these impulses. But the Fourier transform representation of a periodic waveform consists of possibly an infinite number of impulses. If the Fourier transform goes to 0, then there's of course impulses which we present. Here's a result that we'll use when we get actually into talk about sampling and converting analog signals to digital signals. Find the Fourier transform of the cone function. So the cone function, one notation for it is this. It's an infinite sum of shifted impulses. So again, this is our representation of a periodic signal. So this would be a periodic T0, T0, a periodic train of impulses. 3T0 in our code, minus T0, minus 2T0, infinite in both directions. All these would have the same height. And we talk about just a single impulse as being a signal we can't generate in the lab. Physically, certainly can't generate this infinite train. But it's useful mathematically when we start talking about sampling analog signals. We multiply an analog signal by this infinite train of impulses in the time domain. Essentially, got a mathematical representation for the sampled version of that continuous time signal. So it's kind of the first step in going through the math. Now, from this result, though, I want to take the Fourier transform of the basis function. The basis function here is just delta t. It's the function that's between minus t0 and 2 and t0 and t. The thing that's periodically extended. It's just delta t. Since delta t has a Fourier transform of 1, then the Fourier transform of this periodic train from this result is f0 n equal minus infinity to infinity. And the Fourier transform of this thing is 1, So this is 1 everywhere. GNF0 is 1 at all frequencies. Delta F minus NF0. Now, what does this look like? Well, almost has the same form, right? Except it's concept prime. This is a periodic train of impulses in the frequency domain. So with the Fourier transform, looks like again, these would have all the height at F0. One would be 0, 1 at F0, 1 at 2F0, back to minus F0, and this would extend to infinity in both directions. It's kind of an interesting, it's called a cone function. This related cone, I haven't seen a cone in a long time, but if I recall, it's related kind of on its edge with the teeth sticking out, this is something like that. But a Fourier transform of a cone in the time domain is actually a cone in the frequency domain. So kind of an interesting result. We'll see that again later when we start talking about sampling activity. It's getting dark. This is come back into that. Okay. Let's review some stuff from 310 on linear system. Generally, notation, when the input is x of t, we call the corresponding output of our system y of t. T here might be an electrical circuit. The input might be a voltage or current. The output might be a voltage or current, voltage across a capacitor, resistor, inductor, current through something. And there's one specific input that we're interested in. When x of t is equal to delta t, we also have special notation for the output. What's that called? What's the notation that we use? H of t, the impulse response. We can get, if we know the impulse response, we can get, find the output due to any input x of t by carrying out this mathematical operation. This is our input, this is our impulse response. What's this operation called? How do you find the output, given the input and the impulse response? And that's the definition of convolution. That's the convolution. Convolve any input with the impulse response, and we get the output. Remember what the definition of a causal system is? Yeah, what comes after zero? Yeah, there's no out when the input's at zero, there's no output prior. There's no output prior to the input, right? Then mathematically that's fine, but in physical systems, you can't go to a physical system as a response before the input arrives. Mathematically, we can work with non-causal systems. But physically, what's that mean in terms of the impulse response? delta t arrives at t equals 0. H of t is the response to that. What does causality mean with regard to the impulse response? H of t has to be 0 for all t less than 0. So we looked at causality actually in 310 before we got to the impulse response. We had that kind of verbal definition. But then when we got to the impulse response, there's another way to determine causality. Just look at the impulse response. Now, for example, if I had a circuit, I applied an impulse at t equals 0, I got some sort of maybe exponential response that started one second prior to the impulse arriving. That would be a non-causal system. The circuit started generating an output prior to getting an input. It would have to anticipate the arrival of the input or be able to see into the future. You can't build a circuit that does that. Now, on the other hand, if it were a +1, that's okay. It just means, I got this input, I'm going to sit around and twiddle my thumbs for a second, then produce an output. Or it's a delayed output. That's possible. I can't just have an output that's ahead of the input. But in a lot of the systems we work with, the output starts as soon as the input arrives. Not always, certainly possible to have delays. We used a definition of stability. Definition we use in 310 with bounded input, bounded output. That means if the input is bounded, the output is also bounded. If the input never goes above 10, then the output never goes above 20. Really what it's saying is if your input never goes above some certain level, the output is not going to continue to grow with a stable system and become unstable. In terms of the impulse response, the requirement for stability is that the impulse response be absolutely integrable. That the absolute value of the impulse response over all time is finite. Now, if this is a causal system, we would change this lower limit to 0. What was the requirement for stability in terms of the transfer function, the Laplace transform of h of t, which we call h of s? What are the conditions on h of s for stability? I'm going to take a guess. Let me give you another hint. H of s is typically a rational function. No guesses yet. It has zeros and it has poles. The zeros are the zeros of the numerator polynomial. The poles are the zeros of the denominator. Almost. Anybody want to take another guess? Or you want to try a second time? For stability, poles have to be on the left half plane. The left half plane corresponds to decreasing exponentials. The right half plane corresponds to increasing exponentials. But we worked around a little bit with the impulse response. We worked around a little bit with convolution, primarily just so that you would appreciate other techniques for calculating the output, like transform techniques. And we looked at both the Laplace transform. The Laplace transform of the impulse response, we typically call it transfer function, H of s. the Fourier transform of the impulse response we typically call the frequency response. So, and we can calculate the output for a lot of different inputs from the frequency response using Fourier transform techniques. We're going to see how the frequency response actually comes about from the convolution interval. Let's say the input is e to the j 2 pi f0. Now, it seems like a strange input. It's a complex input, right? It's this complex sinusoid. But, you know, the reason we do this is it's nice to work with exponentials. And because of linearity, I know cosine is really, you know, the sum of two signals like this, either the plus j and plus the minus j. You know, 1/2 of that. So if I can figure out what the output is to do this, I can figure out what the output is to do a cosine or sine. So actually, so if I plug this into my convolution interval, I'm going to skip a couple of steps of algebra here. What we get is yt is equal to e to the j 2 pi f0 t interval from minus infinity to infinity of h of tau e to the minus j 2 pi f0 tau e tau. I really didn't skip all that much algebra. You know, this is x, I substituted in right here, so replacing t with t minus tau. I can pull the t term out of my integral because my integral is over tau. So I have t in this case is just e to the j 2 pi f0 t times this thing, which is the Fourier transform actually of h of t, of my impulse response. So times, it's the Fourier transform evaluated at a particular frequency, f0. So now, generally we use Fourier transforms to find the output for much more complex signals, more complicated signals. But let's look at this simpler case. Instead, I've got a circuit whose impulse response is this, it became exponential. Let's say x of t is e to the j 2 pi. I'm going to let the frequency be 2. E to the j. I could write that as 4 pi t, but this, writing it like that makes it a little easier to see what f0 is. It's 2 in this case. Okay, so according to this, with this exponential input like I have here, the output is that same input, just on, this is a constant now. It's the frequency response evaluated at f0. So I need to find the Fourier transform of this. It's 1 over 1 plus j 2 pi f. And I have to take it in. Yeah, that's what I wrote it down. So this is h of that. I apply, in this case, this complex sinusoid that has a frequency of 2. So I want to evaluate my frequency response at 2. I get 1 over 1 plus j 4 pi. Or, you know, I could write this as an exponential form, a polar form. This is going to be square root of 1 squared plus 4 pi plus 16 pi squared e to the minus j. It would be the inverse tangent of 4 pi over 1. The minus because it's in the denominator. So the output is e to the j 2 pi 2t. For this special input, the output is exactly the same signal times this times 1 over 1 plus j 4 pi, or you're writing that this in exponential form, I can write it like this: 1 plus 16 pi squared e to the j 2 pi 2t minus tangent of 4 pi. Arctangent of 4 pi. Any questions about that? You can show, I'm going to skip a few steps here, well, getting to go through this. Then, I can write a cosine as that, 1/2 that, plus 1/2 that with minus frequency. And then so I can get the cosine, the response to the cosine, so you got sum. With a little algebra, you can show that when the input is, let's say, a cosine of 2 pi f0 t plus 5, then the output is the magnitude of the frequency response, the value weighted at the frequency of cosine. This affects the amplitude, and then we've got the same cosine angle plus the phase response of my system evaluated at that same frequency. So this is the amplitude response above, this is the amplitude response, and this is the phase response. So for the same system, with x of t, because I've already done some of the work at this frequency, 2 pi 2t, say plus 30 degrees. Give me a couple minutes to find the output. This same system, this impulse response, more importantly, this frequency response, same frequency response, using this result, and what's the output? You can write it down almost correctly. silly, well, I'll do this first here. This is the amplitude of the input times the amplitude response evaluated at this frequency, at 2. So is the output going to be larger or smaller than the input? Yeah, because square root of 1 plus 16 pi squared is approximately 4 pi, probably, close to that, but which is greater than 1. Since the denominator is greater than 1, the amplitude here is going to be less than 10. So the output in this case is going to be smaller than the input. The circuit's attenuating the input at this frequency. Now, at other frequencies, if I change this frequency, to 5, I have to, I'll have a different amplitude response. I have to go back and evaluate this with that equal to 5. In that case, you can see this will actually be even smaller at higher frequencies. We classify this actually as a low-pass filter. At f equal to 0, this thing actually has a magnitude of 1, and then at higher frequencies, the amplitude response here is actually going to be 1 plus 4 pi squared f squared. So the denominator is going to get larger with frequency, so the amplitude response is actually going to get smaller with increasing frequency. So you call this a low-pass filter. So at higher frequencies, this is going to become even larger, the amplitude is going to become even smaller. It has the same frequency, but then it's going to be plus the phase shift. The phase shift here actually turns out to be negative in this case. Minus 1 plus 4 pi. I don't know what that is. The arctangent of 4 pi. I can give you the tangent of 4 pi, but not the arctangent of 4 pi. Okay, so and this chapter is just a review of some concepts. I think we'll finish up chapter 2 on Friday, but that's it for today.